Okay, can you guys see the screen or not?
Yep, you can see it.
Okay. Okay, I'd just like to point out a couple of typos in the CJ stuff. This should be over 2, not gamma. This is in the ranking Hugonio notes, page 14 and 15. And so basically, I think I had over gamma. It should be over 2. And then MCJ equivalently should be, it should be gamma squared minus 1 over 2, not gamma squared minus 1 over gamma. Okay, so just make those notes to yourself. And then, so fix that. And then let's see, back to the ZND. On page 8, there was a typo here. I had a minus sign here. That's why I was a bit confused on Friday. I had a minus sign here. There should not be a minus sign there. And then basically these terms here, exothermic is if the thermicity is greater than 0, and the thermicity is less than 0 for an endothermic reaction. So all is good with the world. I just said a minus sign there, which is sort of I don't remember whether a positive or a negative thermicity accelerates or decelerates the flow behind the shock wave. I actually look for the sign of this. It's basically how I do it. And so I was confused. But anyways, so that's fixed, just one little typo, a minus sign error. And so other than that, I didn't spot any more typos while I was working through your guys' next homework set, which will be posted either tonight or tomorrow.
Are the notes uploaded on Canvas, correct?
Not yet. I will do that.
Okay.
Okay. So we were discussing the shock structure behind a detonation. We basically ruled out weak detonations, except for a very specific set of conditions that lead to that, and basically requires that at the sonic plane, you have at that exact point you have a switch from exothermic chemical reaction to an endothermic chemical reaction, and that's really the only way to get one of those. And so it's really hard to do. There have been debates as to whether it's been set up experimentally or not. Okay, but then basically, we went through how to find the structure of a detonation by integrating the structure ODEs. Now, it turns out that real detonations, there have some multidimensional effects that in reality, there's no such thing as a perfectly planar CJ detonation that moves downstream. The detonations have like most detonations have curvature, or even gas phase detonations, which I'll discuss as briefly, have cells, meaning that the structure of a detonation, or the frontal structure of a gas phase detonation, is sort of bumpy, and those bumps move around, which produces little cells, and gas phase detonations do that, solids don't. But so there are these really intrinsic multidimensional effects that are important. And so, and one way that they sort of realize this is that they basically use so-called rate sticks, where they have just a cylinder of explosive and they send a detonation through it. And then they basically look at what happens. They basically did these to try to have a very simple configuration where they measure the detonation velocity. Because there's a lot of assumptions that you need to go into it. Like you need a good equation of state, which if the products are at 20 GPa, you don't have a good equation of state for that. And so what they found is that the measured detonation velocity was a function of the diameter of the charge. And what they realized was that if we zoom in to the structure of the shock or the detonation as it interacts with the confiner of the explosive, which could be air, or it could be something soft like plexiglass, or it could be steel, is that the detonation is curved slightly. And this curvature introduces expansion waves. These expansion waves propagate into the chemical reaction zone, and the expansion waves decrease the pressure and they decrease the sort of temperature. And if you think what a decrease in temperature of the Arrhenius term would do, is it would massively decrease the rate of chemical reaction, because you guys saw how sensitive that function was on that Python homework. And so it would massively decrease the rate of chemical reaction to the point where in regions of high curvature, the expansion waves can be so strong that you may even quench the detonation. Okay, so I went over this stuff. And so the reason for a high explosive that you get these sort of effects is that if you have a detonation wave propagating into an explosive, in the reaction zone here, you have the highest pressure in the system right here, or in this region right here. And the pressure here is larger than the yield stress of any confiner. And so basically, the high pressure then basically pushes this confiner away. Well, the pushing away of this confiner introduces expansion waves that can propagate from the side and then go down into, then basically go in and then mess with the reaction zone. And so that's basically where it comes from. And so this is an inherently multidimensional effect, which cannot be taken into account by the Z&D theory, which would assume that that the explosive is of infinite height, and so there is no side for these expansion waves to sort of sneak in. Okay, and so I already mentioned that. And then I guess fundamentally from a gas dynamic standpoint, if you look at the flow from the point of view of the detonation, where the flow of the material is going into the detonation, the curved shock is actually turning the flow away, and there's more curvature here, so it's turning the flow more. This is exactly like an oblique shock, and the flow here, the curvature is not quite as much, so it doesn't turn the flow quite as much. And sort of, and then similar, and then basically so forth. And so basically what you wind up with is this expansion fan that forms behind the leading shock of the detonation. And you got this expansion fan as a result of the continual curvature that basically messes with the reaction zone. Okay, and so you don't even need the pushing away of a confiner to cause the expansion waves to be inside of the reaction zone. You just need a curved shock itself. Okay, and then also you could have the opposite curvature where the detonation is curved inwards, and then the streamlines actually converge like this. And in this case, these streamlines converge, which means you are compressing you are further compressing the material in the reaction zone, and in those cases the detonation actually accelerates, and that's also been found experimentally. Okay, and so you can have both types of curvature. It's just that basically this curvature here, due to basically side losses, is actually much more common. And as I said before, another way to get curvature is through a process called detonation diffraction. So here I have the position of the detonation, or the lead shock of the detonation, as at basically 4 different times. Basically T naught, it's sneaking in this channel here, and then all of a sudden this channel opens up to a big chamber of high explosive, and then this detonation wave will then propagate. The top of the detonation wave will basically propagate basically downstream into the explosive charge, but then the very bottom here will basically turn the corner and then start propagating down. And so this bottom piece here and this top piece here, they'll basically connect, and then the detonation here will be curved. And this process of the detonation sneaking around a corner like that is called detonation diffraction. and the diffraction of the detonation will also introduce curvature. In basically in real explosives that are designed for real things, the curvature near this corner can sometimes be so high that you actually quench the detonation and you have a region of unburned explosive charge. Okay, and basically these are called dead zones. Okay. So are there any questions, at least with the basic concepts of this? Okay, and these do not violate what I said about the Z and D theory. Is that here, what is introducing, or basically what is affecting the reaction zone, is the lead shock itself. If something is happening to the lead shock itself of the detonation, and Z and D theory can't possibly take that into consideration. And in this up here, it's also basically this here is a multidimensional effect, and then basically Z and D theory can't possibly account for that either. Okay, and so basically both of these they don't rule out Z and D theory, but they do violate the perfectly planar shock approximation, and the fact that the Z and D theory only accounts for one-dimensional effects. Okay, and so basically now what we want to do is basically try to correct the Z and D theory to account for this curvature. Okay, and so what we're going to do here is we're going to study curved detonations. And so we're going to just examine an expanding cylindrical detonation. So the detonation is just an expanding cylindrical ring, or it could be spherical. The detonation propagates at some velocity dn. The position of the detonation at time t is given by cap r. So it's just basically the position of the detonation, or the radial position of the detonation as a function of time. And so, and the origin here, or the center of the circle is here, and the distance and the spatial coordinate here is r. Okay, so are there any questions what we are doing here? And so what we're doing here is we're going to ignore any of the sort of side relief processes where the expansion waves sneak in due to the pushing away of solid material. And here we're going to focus solely on the curvature of the detonation. And probably the most easy way to do that, at least the easiest way I can think of, is to study perfectly 1D radial flows. So, and so you have a nice circular detonation or spherical detonation if you work in the one-dimensional spherical coordinates. And so these become a very natural way to study curved detonations. The other way to derive the same equations, which was done by Scott Stewart when he first started this, was to do a whole bunch of crazy geometry and do asymptotic analysis to derive the following equations that I'm going to show you. When I was talking with him, he said it's just easiest to derive them starting from the 1D radial coordinate system, because you get the exact same results in about a fraction of the effort. Okay, and so the motion of the detonation here can be described by the 1D radial equations. And so here we do need to consider the time dependence here, because you can't have a steady radial flow really, because you have no flow, or there's zero flow at the origin. So this detonation here would basically want to propagate away from the origin as a function of time. So we do have to include the time derivative here. But if we take the governing equations that I scribbled down later, or that I scribbled down earlier, and we neglect old diffusive processes, you wind up with this equation here, or these systems of equations here. And so these terms here are the same as the transient planar equations here, and the source terms right here. And so basically, I guess these terms right here are the exact same as the planar terms. And in the divergence terms, you pick up a sort of, it's called the geometrical source term. And it's just basically J over R times the sort of times the flux quantity here. Okay, so for conservation of mass, it's basically J over R times RU, where J here is the coordinate system selector. It's the same one that I showed you earlier. I can't remember what context that was for. But if J is 0, you have a planar system because all these extra geometrical source terms go to 0. If it's 1, our detonation is an expanding cylinder. If it's 2, our expanding detonation is an expanding sphere. Okay. And of course, we're assuming 1D radial flow, so there is no dependence on theta. There is no dependence on theta. So the properties of the detonation are the same along this ray. Oops, they're the same along this ray. They're the same along that ray, and they're the same along that ray, and they're the same along that ray too. Okay, so they are identical. And so this allows us to study these in 1D. Then basically, if you expand out the divergence terms, you get these extra geometrical source terms here. But other than that, these equations are the same as the sort of 1D unsteady planar equations to describe the flow of the detonation structure. So are there any questions with this? Okay, now this system here, we need to study this in basically as a function of time, and that doesn't help us very much. We don't care about the time history. We actually really care about the quasi-steady behavior of the detonation front. So what we're going to do is we are going to make a change, and we're going to make a change of coordinates. And before I do that, just note that the detonation velocity is just given by the time derivative of our dot. Okay, and so those are the same thing. So here in this context, cap D refers to the detonation velocity, which is tradition. So do not confuse that with a diameter of some sort. Okay, and so here we'll make a change of coordinates. Here we're going to take our xt time, or our xt coordinate system, or actually RT, I should say. Our RT coordinate system, and we're going to map it to a coordinate system in the normal direction, and then instead of time, we are going to have tau. Okay, and I'm going to define n as r minus r are the radial position. As recall that in our system here, we had r and cap r was basically down here, and so we are defining n as the radial position minus the detonation position. So we're basically, now we're basically setting, we are setting the origin of our system and attaching it to the detonation front. And instead of the products pointing towards the origin, we are flipping the direction so that the products basically point towards infinity. Okay, so that's basically what we're doing here, and that's achieved by that sign right there. Okay, and I'm defining tau as just time. I do this. I basically do this even when I teach convective heat transfer, where we do quite a few coordinate system transformations. I basically write a completely new set of variables, even if t and tau are identical. It just is to avoid some very common mistakes when we use the chain rule to convert derivatives from one coordinate system to the other coordinate system. Okay. So what you wind up with, if you do a very formal coordinate system transformation, and that's part of your project 1, so I'm not going to go through the details of that, but you go through a very formal coordinate system transformation, and what you find out is in the system, we have partial rho, partial t, It's just that partial t is equal to 2 partial tau. So we have the time derivative of rho with respect to t plus partial rho partial capital U. Oh, and this capital U is the flow velocity with respect to the detonation velocity. Okay, and so we basically are just shifting our coordinate system from an expanding circle to an almost planar system, with the exception that we have these extra geometrical source terms here that account for the expansion behind the detonation charge, or behind the detonation front. Okay, and so what we wind up with for conservation of mass is we wind up with the fairly normal looking terms here for the density and for the and for the flow velocity relative to the detonation charge. So basically, we're just looking at a stationary detonation, and then we're casting it into a 1D like, or a planar like form. But we do have to add, but when you do the transformation, we do wind up with this extra source term that accounts for the curvature, effects of the detonation. So, and so up to here, this equation here is actually exact. This is just conservation of mass in this flipped coordinate system right here. Okay, and so, and you can do the same thing for all of the other equations. And so right now, this didn't gain us very much. You still need to solve it in a steady form and all that stuff. So now what the theoreticians assumed was that they assumed that the curvature that the length scale of the curved detonation is gigantic compared to the length scale of the reaction zone, or basically that this reaction zone here is very thick in comparison to the sort of radius of curvature of our curved detonation. And that sort of makes sense because some of for some explosives, the thickness of the reaction zone is on the order of, tens of micrometers. So it's it is very, very thin for a lot of explosives. And there are certain classes of explosives where the reaction zone is much thicker than that, and this theory starts to fall apart if you have those types of explosives. Okay. So then, basically, this theory is valid if the length of this reaction zone is much, much smaller than ours. So we're going to start making those assumptions. And just note, I'm not going to prove it, but the curvature of the shock front is just given by J over cap R. Okay. And so if you recall, for a cylinder, the curvature is equal to 1 over R for a cylinder. And for a sphere, the curvature is given by 2 over R. Okay, and so basically this formula works. And then, of course, if you have a 1D planar system, you have no curvature. And so we're going to demand, and so as a sanity check for the equations that we derive, we're going to demand that if there's zero curvature, the equations recover the 1D planar form that I have scribbled above. Okay, so now, and if you notice here, these source terms, and there are similar source terms for all of the other equations too, and they all have, they are all multiplied by this J over the coordinate in the normal direction over capital R. Okay, so, but if the length of the reaction zone is much, much smaller than the radius of curvature of the detonation, then we can assume that we are only going to integrate, our integration is going to go from here to here, which means that physically our coordinate direction n, I should probably write that, our coordinate direction n is also going to be much, much smaller than R. And so we can simplify these j over n plus r terms here by really assuming that n is much, much smaller than r. You can do this one of two ways. You can do a formal Taylor series expansion and expand j over n plus r and assume small and expand that for small n, and you get j over r minus j times n over r squared, blah blah blah. And if we only take the first term, because we are assuming small n, you get j over r, which is just the curvature. And so basically here this just becomes the curvature. So we can say that j over n plus r is approximately equal to j over r, which is equal to the curvature of our detonation front. Or alternatively, you could do this very directly by just arguing that, well, if we are arguing that n is much, much smaller than r, then you can just assume that, then you can just cross out n right there, and you wind up with this directly. So basically either way works. It just depends on your point of view of how you approach simplifying equations like this. Okay, and so now what does this buy us now? So we've gotten rid of, what this does is this gets rid of the spatial dependence on the source term. And so the source term here, if we basically approximate this entire term here as just the curvature, and it's the curvature of the detonation front, not the local curvature of the flow, but it's the curvature of the lead shock of the detonation, and that's just a constant, is that you basically pick r. And so if you make the substitutions and say that this j, I really wish I had more panes to work from, but I keep going up and down, sorry about that, is that if you approximate this using our Taylor series expansion, where this here is just the curvature or kappa of the shock front, we wind up with the conservation of mass becoming the time derivative of density plus the divergence of the flux in our relative coordinate system, plus the curvature times density times this u plus the detonation velocity. And I'll get rid of this n here. Okay, so that's basically the theory basically assumes that we have small curvature relative to the length of the reaction zone. And so if we repeat this process and go to conservation of momentum, which again is part of your guys' project 1, is we wind up with this equation here. And so these terms here that I'm circling are part of the normal conservation of momentum for the flow behind the shock. And we actually wind up with this really interesting term here. This theory, the full theory, if we use it all, it actually can account for this this dt is actually shock acceleration or detonation acceleration. Okay, so it describes the acceleration of the detonation. Okay, and so we can account for things like that. And then there is also the curvature term that is induced by the basically curving of the streamlines behind the detonation charge. And again, we are assuming that the length of the reaction zone is so small that the curvature effect is described or is basically defined by the shock itself and is held constant. Okay. And if you do species mass is unchanged. In energy, you basically wind up with this equation here, where basically we need to be careful. We need to convert the normal stagnation enthalpy to the stagnation enthalpy in our coordinate system, and so you need to switch both the derivative terms and also and then also account for the flow velocity. Okay, but it is really really just a bunch of it's really a calculus exercise after this point. After you make the ansatz that the length of the reaction zone is small relative to the curvature. Okay, but basically now what these equations here are is that if you do the procedure for a planar detonations and cast them into primitive variable form, you can actually get versions of the structure, versions of the ODEs that can be used to describe the structure of a curved detonation. Okay, and note that in general we have these acceleration terms which are dd dt, and the general detonation shock dynamics theory can actually handle the acceleration of the detonation because those terms are present in the structure equations. But I'm not going to go through that portion of the theory. That gets a little bit intense. Okay, but just note that it can handle that. And so if you're to assume steady state, these and ignore acceleration of the detonation, the structure ODEs for the detonation are for the flow behind the flow behind the leading shock front, basically turn into this. And so we actually have very similar equations to what we had before. We have conservation of mass right here. I just moved the curvature term to the right-hand side. We have conservation of momentum. I just moved the curvature term to the right-hand side. And we're assuming no shock acceleration, and we're assuming steady state conditions. So we don't need to, so basically all the time derivative terms get canceled out. We have the acceleration of the flow relative to the shock wave. This equation is actually unchanged from the planar version, with the exception that the thermicity accounts for the curvature effect. So basically, we have an acceleration of the flow by exothermic chemical reactions, and that is being counteracted with the sort of deceleration of the flow due to curvature. Okay, and then eta is the same, and then the change of the mass fraction. Change of the mass fraction is the same, but with the exception of these curvature terms, these equations here are identical to the planar versions. And so if you set kappa equal to 0, you recover the planar version. And so that is just a sort of good sanity check on our theory that it at least works for the major limiting case that we care about. Okay, and so, and again, so not only, as I said before, not only does thermicity account for changes in density and flow acceleration due to the chemical reaction through the chemical reaction portion of the thermicity, it also accounts for deceleration due to of the fluid by curvature, and that's through basically this term here in the thermicity. And so for planar detonations, kappa is equal to 0. And so if we demand that sigma dot is equal to 0, that means that the rate of chemical reaction must be 0, right? And so that's sort of what gave the sort of Chapman-Jouguet detonation condition, was that sigma dot was 0 when eta was 0, and sigma dot being 0 required that there's no net, or that the rate of chemical reaction is 0, which means you are physically at chemical equilibrium. Now, for curved detonation, that is no longer the case, because if you have kappa greater than 0, that is the detonation is sort of expanding. You still require for a stable detonation, you still require that when eta is equal to 0, you require that this modified thermicity is also 0. So that fundamental condition still has not changed. It's just that basically what makes sigma dot 0 is basically different now. And so we have this extra term here that is due to the curvature, that is induced by the curvature. Well, and basically this term here can never be 0 unless kappa is 0, because the speed of sound is never 0. The flow velocity behind the shock wave is never 0. If you have 0, if U is 0, that means there's no detonation, and the solution becomes trivial. and the detonation velocity is also greater than 0. So basically this term here, or basically these terms here that I have circled are always positive. Kappa can be negative. This can account for a cylindrically imploding detonation, which there are reasons for that. I'm not going to get into that in this class. But for curved detonations with kappa greater than 0, if we demand that basically sigma dot and eta approach 0 at the same time, to avoid the solution from blowing up, we require that basically we require that the sort of net thermicity of due to the induced by the acceleration by the chemical reactions is balanced by the curvature term exactly. And so essentially the process is identical to finding the structure equations, or to integrating the structure equations for planar detonation, with the exception that we got this extra curvature term here to sort of deal with. And so, but now what this means is that we now have conditions where the detonation can be in equilibrium, meaning that both of these are 0, and there's no acceleration after that point, but there are still chemical reactions occurring at the sonic plane. So what this means for curved detonation is that the products exiting the sonic plane of the detonation are partially reacted. They are not fully reacted anymore. Okay, and so if we plot, this should be y. So if we plot the mass fraction of the reactants behind the detonation front, we have the shock here. And just prior to the shock, it's the pure reactant state. And so for the planar detonation, the change of mass fraction could look something like this for an explosive, or for a gas, it looks something more like this, more asymptote to 0. But for an explosive, it'll look something like this. And so for a planar detonation, the mass fraction of the reactants will go to exactly 0 at the point where eta is equal to 0. That's just part of how it is. And then, but for a curved detonation, what happens is that due to the extra curvature terms, is that the sonic locus will occur before all of the chemical, or before the reactants are depleted. And so basically what that means is that there's still some reactant left over. And that's just basically due to the modified thermicity, which is now modified to account for the curvature effect. Okay, and so there's still some reactants left over after the sonic locus. And so those can do some weird afterburning things and things like that, but they can't really influence the propagation of the detonation, is because we have that sonic locus. And I call it a sonic locus for these curved detonations because it's no longer a plane, it's sort of a curved thing. So it's a sort of, it's more of a more complex curve than it is for a planar detonation. So for a curved detonation, the sonic plane is traditionally called a sonic locus. Okay. So, but there is an issue with this, is that for given values of, say, a detonation velocity, there is only one value of the curvature that will give a stable, or what will give an equilibrium detonation. So you're not free to pick D and kappa to be anything you want. Is that there is a correct, there are correct pairings for the detonation velocity and the curvature of that detonation. Okay, and so this here actually becomes what's called an eigenvalue problem. And the issue is it's not a Chapman-Jouguet detonation anymore, and so we don't have that extra tangency condition to apply where the Rayleigh line and the product Hugonio basically touch at exactly one point and their slopes are identical. We don't have that extra condition anymore. And so what we need to do then is we need to integrate the structure equations and then directly, and then check and see if sigma dot and eta go to 0 together. If they go to 0 together, that means we have satisfied our equilibrium condition. If sigma dot goes to 0 before eta, we have not satisfied it. If eta goes to 0 before sigma dot, we've also not satisfied it. And so it becomes a bit more involved. And so you need to integrate the structure equations. And so if you say you are given a value of d, you need to find the value of curvature such that you can find the equilibrium point. And the equilibrium point is where sigma dot and eta are both 0 at the same point in the flow. You don't know where that is, and you don't know what the and you don't know how much unburned stuff there's going to be left over after that point. Okay, and so and basically doing that is part of project 1. But after you, and there's a very sort of nice sort of algorithm that you can do for doing that. It's based on bisection and it's robust as hell. If it fails, it isn't due to the bisection method going crazy. It's just due to the ODE solver going basically going nuts. Okay, and so here I just have some d kappa curves just sketched for a couple of basically 2 typical curves, styles of curves that you see. The one that you'll see from your project is the one in the black line, where basically we are plotting d versus kappa, and what you'll find is that if you set kappa equal to 0, you should exactly get dCj, which you should. Then as you increase kappa, you slow the detonation more and more and more, and eventually you get to a point where it starts to turn, and the solution to the structure equations will actually turn, and you'll get this sort of weird branch here. And this here is mathematically unstable. It corresponds to a saddle point, and so these are really never observed. And so if you have an explosive that produces a sort of a P-shaped curve here, what will happen is if you start with, say, a planar detonation and you diffract it around a corner, and the curvature keeps going up, well, you're going to slow the detonation down, and eventually it's going to go to this point over here. It's going to follow this curve, and then it's going to fall off a cliff, and you extinguish the detonation. And so it basically no longer lives, because this here is an unstable branch. These solutions can't live there, even though mathematically they can in theory. But again, it's like trying to balance the ball on the top of a valley. And the other type of curve that is commonly seen with these types of things are the orange S-shaped curves that basically look like this. And these ones, the explosive that I have you working with for the project does not do this. It does this. And the top part of the S curve looks identical, and the unstable branch looks identical. But after a certain really low detonation velocity, it starts to curve around and goes, and then basically go the other way, and basically go like that. And so what basically this type of curve gives you are sort of ignition and extinction cycles. So if we start from a detonation here, a planar detonation, and we just bump up the curvature, we'll follow along this orange line till we until we get to this point here. Then we can't go in, then if we increase kappa further, we jump down, we have to suddenly jump down over to this line over here. And this here corresponds to an extinction branch where it's just a propagating shock wave with some burning stuff behind it, with a very modest amount of burning behind it. Now, if we go the other way, if we start over here and we decrease the curvature, meaning we make the circle is that a very small circle becomes more and more planar like, eventually what happens is we follow along this curve over here, we keep following it, and we start to turn. And then after we get to this point here, we jump back up to the detonation branch. And so basically this here sort of predicts basically detonation, propagation, extinction, and ignition cycles. And so it's actually fairly interesting. And this point here, but again, but to properly do the detonation, extinction, and ignition, we need to use a more complicated theory that we're not going to go over in this class. But this point here is relevant, and this is the critical curvature. The detonation will not propagate if kappa is greater than this critical curvature. Okay, and so so we'll go over that stuff, but I'll scroll back up to the top of this. Is that the theory predicts curves that look like this. Now, if you look at the experimental results that I showed earlier, is that they actually have this exact same type of curve. Is that they behave identically, and not surprisingly, the experiments, because the detonation fails, they do not capture the sort of bottom part of the curve. They do not capture this period. Okay, and so this type of behavior, where it's sort of flat and linear at the top and it curves down to the critical point, is also observed in experiments. Okay, and so that's all I will go over for today. And again, sorry for the computer issues, but that is what it is. So